Hi, I'm Matt D. This is Math 3DU, and today we're going to talk about the substitution method.
We've already seen that one way to solve a system of equations is by graphing. Sometimes, though, the substitution method is a much faster way to solve those same systems. Let's start with this system of equations. Y equals x minus 3 and 2x plus y equals negative 6. Graphing these equations wouldn't be that difficult to do. However, it may take a lot more time. Instead, we'll use the substitution method. The substitution method is used when at least one of the equations has a variable, x or y, that is isolated. You plug the expression equivalent to the first isolated variable into the second equation and solve for the second variable. Once you have the solution for the second variable, you can then plug it back into the equation for the first variable. Let's see an example. Going back to our system, y equals x minus 3 and 2x plus y equals negative 6, we can substitute y equals x minus 3 from the first equation into the second equation to get 2x plus the quantity x minus 3 equals negative 6. Simplifying gives us 3x minus 3 equals negative 6. We can then solve the equation for x. We first add 3 to both sides to get 3x equals negative 3. We then divide both sides by 3 to get x equals negative 1. Now that we have a solution for x, we can solve for y. Let's use the first equation, y equals x minus 3. Plugging in x equals negative 1, we have y equals negative 1 minus 3, or y equals negative 4. So we can verify that our answer to the system of equations would be negative 1, negative 4. This system has only one solution, so we can call the equations linearly independent. What happens when you don't have an isolated variable? Solve for it. Our system of equations is 2y plus 2x equals 10, and negative 6x plus 2y equals 2. Let's solve the first equation for y. We first subtract 2x from each side to get 2y equals 10 minus 2x. We then divide both sides by 2 to get y equals 5 minus x. We can then plug this into the second equation and solve for x. Using negative 6 plus 2y equals 2, we plug in y equals 5 minus x to get negative 6x plus 2 times the quantity 5 minus x equals 2. We first distribute the 2 to the quantity 5 minus x, giving us negative 6x plus 10 minus 2x equals 2. Adding the x's together, we have negative 8x plus 10 equals 2. To isolate x, we subtract 10 from both sides to get negative 8x equals negative 8. Finally, dividing by negative 8, we have x equals 1. Once we have x equals 1, we can then plug it back into the first equation to get a solution. Using y equals 5 minus x, we plug in x equals 1 to get y equals 5 minus 1, or y equals 4. We can verify that the solution is 1, 4, and that the system is independent because it only has one solution. Now that we have the basics, let's try a story problem.
Matt here is running a lemonade and corn dog stand to pay for college. Let's see how we can introduce a system of equations into this situation.
Hi, I'm with the local government. I just came to check out your shop, and I noticed you don't have a permit for selling these goods, so I'm going to need to go ahead and audit you. So I'll need to know the information of your total sales in your lemonade and also the total sales of your corn dogs.
Matt's worried because he didn't count the number of corn dogs and lemonades that he sold. Luckily for him, a system of equations will take care of this problem.
What I do know is how many total items I sold and how much money I made. Using this information, we can make a system of equations that can tell us how many lemonades and corn dogs I sold. First, we'll equate the number of items sold. We'll let L represent the number of lemonades and C represent the number of corn dogs. I made 5 transactions, so our equation is L plus C equals 5. Next, we'll equate the money I made. The number of lemonades times the price of the lemonades plus the number of corn dogs times the price of the corn dogs equals the total price. The price of the lemonades was 50 cents and the price of the corn dogs was $1. I made $4, so we can write this equation as 0.5L plus 1C equals 4. From here, we can solve it as a regular system of equations. First, we'll solve our first equation for C. We can subtract L from both sides of our first equation to solve for C. By subtracting L, this gives us C equals 5 minus L. We can then plug this equation into our second equation and solve for L. By plugging C equals 5 minus L into 0.5L plus 1C equals 4, we get 0.5L plus 1 times the quantity 5 minus L equals 4. By distributing the 1 to the quantity 5 minus L, we get 0.5L plus 5 minus L equals 4. We can then add like terms together and get 5 minus 0.5L equals 4. We can solve for L by subtracting 5 from both sides of our equation to get negative 0.5L equals negative 1. By dividing both sides by negative 0.5, we get L equals 2. Once we know what L equals, we can go back and plug this into our first equation to get C equals 5 minus 2. And this gives us C equals 3. So, we know that in the end, I ended up selling 2 lemonades and 3 corn dogs.
Now let's see what happens if his price is changed.
Now we'll make a system of equations to meet our new conditions. Our first equation doesn't change since I didn't sell any more items. So we still have L plus C equals 5. Our prices for the second equation do change. Lemonades now cost $1 and corn dogs still cost $1. I made $5 this time, so my second equation is L plus C equals 5. You can probably already recognize that this system is linearly dependent, but we'll try to solve it anyways. So first, we're going to subtract L from both sides of our first equation. This gives us C equals 5 minus L. Once we have this, we'll plug it into our second equation and solve for L. So we have L plus the quantity 5 minus L equals 5. Now we'll add like terms together and we get 5 equals 5. Now the result 5 equals 5 is a true statement. So our system is linearly dependent, meaning that in this situation, there are multiple solutions to our system. This means there's no way for me to determine how many corn dogs and lemonades I sold. I could have sold 3 lemonades and 2 corn dogs, or 4 corn dogs and 1 lemonade. I guess I'm in trouble this time. On a side note, if this statement was false, our system would be inconsistent and there would be no solution.
Unfortunately for Matt, this system of equations is linearly dependent. There are multiple combinations of lemonade and corn dogs that could have given him $5. So there's no way for him to be sure how many he sold of each. Let's see what happens when someone makes a mistake.
So let's make another system of equations. Yet again, our first equation doesn't change. So we have L plus C equals 5. Now recognizing that we went back to our original prices, let's form our second equation. We have 0.5L plus 1C equals the total amount of money I made. Checking my cash box, I see that I only have $3.75. So my second equation is 0.5L plus 1C equals 3.75. Now we can solve it like any other system of equations. Let's start by isolating C in our first equation. We'll subtract L from both sides to get C equals 5 minus L. Now we'll take our equivalent expression for C and plug it into our second equation. This gives us 0.5L plus 1 times the quantity 5 minus L equals 3.75. Distributing the 1 to the quantity 5 minus L, we have 0.5L plus 5 minus L equals 3.75. Adding like terms gives us 5 minus 0.5L equals 3.75. Subtracting 5 from both sides to isolate L gives us negative 0.5 L equals negative 1.25. To solve for L, we divide both sides by negative 0.5, and this gives us L equals 2.5. We then plug this back into our first equation for C to realize that C equals 5 minus 2.5, or C equals 2.5. The solution to this system says that I sold 2.5 lemonades and 2.5 corn dogs. I got a fractional solution, but I only sold whole corn dogs and lemonades. There is no possible amount of whole corn dogs and lemonades that I sold that would give me this amount of money. I must have lost some money somewhere, and now I'm in deep trouble.
While I didn't make enough to pay for college yet, we did see how the substitution method can be used in a real-world example. Thanks for watching, and thanks for learning with us.